Hello, everyone. My name is Stephen Slaughter, and thank you for attending the USGS Landslide Hazards Seminar. This meeting is hosted by the Landslide Hazards Program and co-organized with contributions from Matt Thomas and Jamie Kostelnick. For those of you who are new to the meeting, you can submit questions via the chat window or use the raise your hand feature in combination with your microphone and video camera. We'll wait until the end of the presentation to take questions. During the presentation, please keep your microphone muted and your camera turned off. Today's speaker is Philip Prince. Philip earned his BS in 2004 at Furman University in Earth and Environmental Sciences. He completed his PhD at Virginia Tech in 2011, researching Appalachian geomorphology. Philip taught at Virginia Tech until 2016, and then went to the Virginia Division of Geology and Mineral Resources to be a geologic mapper, where he still works. In 2019, he also joined the Appalachian Landslide Consultants, where he also works. And if it isn't apparent by the end of today's presentation, Philip is a huge fan of LiDAR. So Philip, the virtual stage is yours.
Okay, thank you, Stephen, and thanks everybody for joining us today. And yes, LiDAR has become a big part of my both professional and I guess sort of hobby life. And I'm always very excited to tell you about it and how I and colleagues have been using it over the past few years to try to get a better understanding about slope movement here in the Appalachians. And to kick it off here, give you a look at this incredible feature on Catawba Mountain in Virginia. The age of this thing is unknown, but it's a monster rock slide to sort of rock avalanche type of event. If you imagine the slope being sort of restored there, failing into that present geometry, a lot of material has moved. And when you think about the physical size of this thing, a little over 800 meters long there, 2,750 feet, better part of 300 meters, 1,000 feet wide at the top. Just the gap there in elevation from the summit of the ridge to the flat there is almost 100 meters. So it's a very substantial feature, but I choose it to start with because it's one whose evolution, whose appearance today is very much a product of the bedrock geology and the structure here. So if you cut that thing away to a block diagram, you'd end up with something like this, where there's very steeply dipping sedimentary bedding. The light blue there is the principal ridge-forming sandstone. That's a Siluro-Devonian age sandstone. And the failure has removed a big chunk of that and a little bit of underlying stratigraphy to make that huge deposit. Now, what I've drawn here is pretty much to scale. The deposit there would be at its thickest 30 meters or so, just estimating from what the surrounding topography without such a deposit looks like. So about 100 feet thick, and a lot of that, of course, is that light blue debris with those underlying layers mixed in. And in this particular case, that strong, weak mechanical arrangement within that slope is what's driving this failure style. So in this particular case, on Catawba Mountain, there's a lot of these things. I chose the one here, I think that's the sort of the most extreme example, but that whole ridge is littered with failures like this. Again, age unknown, but at the end of the day, the mechanical elements here dip much more steeply than the slope. Extreme mechanical contrast, so you got some weak material in there at a much steeper angle than it normally would be were it not propped up by that cap rock. And that at some point in maybe Pleistocene to present geologic history produced that really exceptional failure. That type of thing can be represented in a physical model. If you've seen anything I've done online, I'm a big fan of analog models, and we can start a slide block moving here. Sort of starts breaking apart. You can see a couple intact blocks left there, and you move it even further. One more intact block survives, and ultimately you get this, again, sort of avalanche style deposit. It has these kind of lobes within it there. How did you make this happen? Well, it's got a really steep, weak layer buried underneath a much stronger, more cohesive sequence. And as that failure occurs, the failing mass is sort of forced through a bend, going from that steepness out into a flatter slope, and that causes the block to break up, and you end up with that sort of avalanche style deposit. And looking at a feature like this, you can actually go to this in person and look at all these different rock types that are controlling this type of failure, and get a sense that certainly in this case, in the Appalachian Valley and Ridge, where rock contrast is sort of what defines it, that's what makes the Valley and Ridge, that's very clearly a significant contributor to this style of failure. And in this particular case, this big highly mobile sort of rock avalanche style is where you got 50 or 60-degree bedrock dip within a slope whose overall bulk slope towards the upper part of the ridge here would be in the, the 20s or the 30 degrees. So with bedrock dip being much, much steeper than the topographic slope, you can force that failing mass through that flattening bend, break it all to bits, and take all that potential energy and turn it into this big huge rock avalanche deposit. Now, the interesting thing about this failure style is that you see it throughout the valley and ridge if the structural geology and stratigraphy are right. What you're looking at here is Walker Mountain. This is probably, I would say, something like 40 miles, a little over 60 kilometers southwest of that failure that we opened with. And if you're looking at that LiDAR, you may see some similar sandstone bedding on the ridge. We'll wake the pointer up right there. And you might even notice evidence of some big failures that look the same way as well. We can highlight their deposits there. Almost exactly the same size. The larger one there to the lower left is about 700 meters, about 2,300 feet from head to toe, but generally the same stratigraphy. It's the same stratigraphic interval, dipping at 50 to 60 degrees with the bulk slope steepness being less than that. And you get that same type of behavior there, right? To the extent that, you can draw a pretty good comparison between the morphology of this big deposit and the failed area and to the slide that we started out with there. You can take it beyond Southwest Virginia in the Valley and Ridge. This is actually a Lost River, West Virginia, a little bit further to the foreland in the Valley and Ridge system. The stratigraphy in this area is a bit different, but generally speaking, you still see extreme topographic control by a particular sandstone layer that has some much weaker shales mixed in with it, and they are essentially propped up into what is sort of an intrinsically unstable geometry. Now, you may wonder, why is there this big patch of forest out in these nice farm fields? And if you throw the LiDAR on that, it's an absolutely monster, sort of, again, rock avalanche style of deposit. This one's really interesting to look at sort of along the trend of the ridge. It's also probably pretty thick. If you compare the top of this deposit pile to elevations here on the floodplain, I would estimate 25 or so meters, 80 feet thick, something like that. When you look at it from this direction, you can see that it also was quite mobile. And it ended up as a very shallow deposit, suggesting that it really hit the ground running. It's big as well. You can see these blocks of some sort. I actually don't know. I presume these are boulders or discrete pieces of sandstone. They have an unusual rounded outline, but the one pointed out by the arrow there is about 20 meters across. And of course, you can fit a whole lot of those onto that deposit. The entire deposit would be something like 500 meters, almost 1,700 feet across. Similar type of scenario, very steep bedrock dip here. This is on sort of on an anticlinal forelimb. And when failure occurs here, and those weak layers that provide a detachment surface, presumably here some sort of a shale, when they lose the support of that sandstone, it's going to be a very rapid and energetic event. Now, an interesting contrast to draw is between the failures we've seen so far and the one you're looking at here. Again, if you've seen anything I've written online, you've probably seen a picture of this. I've been looking at this thing, I think, since about 2017, really since the 1 meter LiDAR for Southwest Virginia came out. Absolutely incredible translational block slide. Same stratigraphic intervals, Siluro-Devonian sandstones sliding on weaker shales. Again, quite large, hundreds of meters across, even a little bit longer from head to toe. But this feature is moving on an extremely gentle slope compared to what we've seen so far. And in fact, the slope that you're looking at here is almost a perfect dip slope. Now, dip there is about 18 degrees, kind of an exact estimate. It's not an estimate. I actually mapped this quad last year and I walked all over that slide. I'd love to show you a representative picture of it. It just looks like thickets of mountain laurel, almost to a greater extreme than is normal in this area. It's like the the shallow hydrology or something has been altered a little bit by displacement. And it's also so big that you can't, readily take a good picture of it. But all that to say, at that low dip, movement is possible, but it's going to be in a very different regime from a failure in a similar stratigraphy, I'll say, where the dip is much steeper. And I don't think you could get behavior like you see in the inset there at Lost River, where dip is much steeper, out of that gently dipping Walker Mountain slope. Interestingly, I would tell you that big landslide at 18-degree dip there, I would tell you that's active. I would say that if you could have monitored that over the last century, you would see appreciable movement, at least at the toe. That's based on what the ground surface looks like at the toe of the slide, impacts to vegetation, things like that. Again, that's creeping, episodic. Who knows how long that feature has been moving along. But fundamentally, the mechanical details are making its behavior very different from similar rocks in very dissimilar orientations. And the valley and ridge is a good place to start with all this, just because the mechanical contrast in the lithologies there is so extreme, and the variety of orientations there is very extreme. But if you go throughout what we see today as the remnants, if you will, of the Appalachian origin from Piedmont to Appalachian Plateau, each of those areas has a distinct topography, and that distinct topography is a product of the bedrock and its structures in those given areas. If you were to cut the Appalachians open, we'll say roughly along a line of section like this, end up with something like what is portrayed with this diagram. I leave myself an artistic attribution here. I'm a big fan of Microsoft Paint, so I tried to put this thing together just because I'm usually not able to find a good enough sort of origin scale cross section that shows the elements I want it to. But basically what you're seeing here, Piedmont, Blue Ridge, they're separated actually by a little Brevard fault zone there, which is that light lavender color. Valley and ridge, folded and thrusted sedimentary rock, much of it being the same stratigraphic interval along this line of section, which is something you see in Tennessee. Limestones dominate. There's actually not a lot of ridge topography there. Moving north into Virginia, a lot more sandstone is worked into there, and you get bigger ridges there. And then you got the Appalachian Plateau out past that, which is basically flat lying or maybe warped sedimentary rocks. But plateau and valley and ridge have very extreme mechanical contrast between, for example, quartz aeronites and shales. The Blue Ridge has reasonable potential for lithologic contrast. It's possible to see pretty quartzose materials, particularly, of course, when they're metasediments in the Blue Ridge. Piedmont rocks, in many cases, are quite aluminous, sort of schistose rocks, and there's a lot of amphibolite there as well, metabasaltic rocks. The Blue Ridge escarpment, which is a feature you're going to hear about here, sort of sits on the boundary between the two, but it actually occurs in both the geologic Piedmont and the geologic Blue Ridge. If you fade those colors away and look at structural elements and composition-related orientation, the Piedmont tends to be pretty low dip, sort of nap type structures of 10, 15, maybe 20-degree dips. Across the Brevard zone of the Blue Ridge, dips tend to be steeper along compositional layers. Now, these are foliations, but systematically steeper, 30s plus. Valley and ridge, it's across the board. And of course, the plateau there is a very low dipping area as well. So again, each of these areas has a distinct character, a distinct sort of independent variable framework in which slopes have evolved and in which those slopes continue to evolve through, among other things, failure events. Everywhere you got here, steep intersecting joints, exfoliation joints as well. All of these provinces have them. It's not really possible to render those, of course, in an image like this. So today, we've already looked up there and right there in the valley and ridge. I'm going to sort of take a tour across other parts of the Appalachians here. And again, this is sort of the synthesis of my own experiences looking at landslides over the past several years and actually field checking features that are at first remotely identified by looking at LiDAR. So moving south, we're going to look at Piedmont that still has some rugged topography, Blue Ridge, and then the Appalachian Plateau. And if you wanted to just take a broad brush view of these different landscapes and what they look like, you could just use Google Maps terrain. It's not quite LiDAR scale, but the spatial patterns are there. There's your valley and ridge. This is your Piedmont, still with some rugged topography, like you see right here in the center part of the screen. Blue Ridge Escarpment exposing Blue Ridge rocks. That's that particularly dark, rugged area right in the center of the screen. And Appalachian Plateau, where a sandstone cap rock has these incredible gorge systems, these dendritic gorge networks incised into it. And in that circle right there is what we're going to finish. Going to finish the talk on it. Sort of an interesting detail. I just picked this place sort of at random as a representative plateau topography. And it's interesting to look at what that turns up in terms of slope behavior. But starting off here, we'll look first at some of these Piedmont examples. So LiDAR of a forested slope here. This is in Rutherford County, North Carolina. You can actually faintly resolve in the LiDAR some of the discontinuities up there towards the top of the ridge that define foliation. It would be faintly southeast dipping, sort of like you see here. And there's actually a big bedrock failure in this image. You almost can't see it. There's a big flat on a slope there. The displacement is low, and the biggest expression of it actually is inside the mountain. There's big dilated joints that you can actually walk around through. But because of that bedrock orientation within this area, there are substantially fewer big rock mass slides like we were looking at the valley and ridge. Big is also relative. That's about 175 meters across. Absolutely dwarfed by all of the valley and ridge slides that we looked at starting the talk out there. This area is interesting because a lot of the slope failure here is actually in deposits produced from outcrop zones of some of these kind of low dip structural units that ultimately cap topography. I'm going to fade the LiDAR in here, but just for your reference, you'll notice that where the pointer's moving around, this area has been logged, and it's been logged within probably the past 20 years or something like that. There's a pretty distinct demarcation where the cutting stops, and if you fade LiDAR, that cutting stops where the slope starts to get a whole heck of a lot steeper there. Interesting arrangement here. Again, very shallow dipping structural elements define this topography. You can almost make out some of the outcrop bands on the slope there, but there is a very prominent slope failure that's being highlighted there. And there's another one that you can see just up above it, sort of that lumpy and hummocky signature there in the LiDAR. Up towards the top of the slope where rock is in outcrop, sort of a cuesta-like system, low dipping resistant layers that locally produce cliff bands. That outcrop zone is pretty extensive. It tends to be quite extensive along the trend of the mountain. And in some respects, it does resemble a topographic feature like a cuesta that you might see in the Western US. The distinction is upper amphibolite facies metamorphics, and it's actually often very difficult to determine what mineralogic detail about the lithology is making that resistant material so much more resistant. But regardless, it sheds colluvial debris and has been shedding that debris presumably for a significant period of time, and you end up with this weathered colluvial apron. Slopes are pretty low down there, less than 20 degrees. And the slide there itself is, again, it's also not very big. If you compare that to the slide we started off with, 100 meters versus about 800 meters, and actually you can load up here 1-to-1 comparison. These are at the same zoom, same scale. Not a whole lot of comparison between the scales of the systems. At the tip of the black arrow down there, if you look closely, you can see two little dimples, and those are the flats associated with that first huge kind of rock avalanche feature I showed. You can imagine taking that thing and kind of placing it within this kind of brick colored outline here. It would be really big. I mean, you would literally be able to see it from this zoom in Google Maps terrain. If you looked at this view, I mean, it would dominate the screen. So the physical scale of the slopes and particularly the failure that we're talking about here is quite different. But this is a really interesting one to look at because it is a debris slide. The conceptual model here would be that highly weathered colluvium of unknown age, presumably it's been there for a while, is slowly but surely translating down slope. It's likely that shallow groundwater, potentially atop the bedrock surface, is helping that along. And if you looked at it in the real world, you would see back rotated trees up there around the headscarps. You'd see trees getting pushed over down at the toe, where the toe is kind of riding up and out of that deeper slide plane. Things like tensile cracks above those toe thrust features are often visible as well. So that is the model here, and you're going to see that several times. The way I put these talks together, I guess I'm trying to like kind of build up a pattern and allow you to see that this type of failure is actually quite representative of this area, which we mapped in pretty good detail in about 2021. I think it might have run over into 2022. Now, what would you see if you actually went out and looked at this slide in the field? First of all, it would look different from the LiDAR. It would have a new toe, which is down here at the bottom, and it would have what I would call, I guess, accentuated internal headscarp, internal extensional scarp. Went here with colleague Ken Gillen back in the summer of 2021. What does that new toe look like in the field? Well, it's a 3 or 4 foot tall wall of colluvial soil that is being pushed up out of the ground by the downslope motion of the slide. If you get Ken out of the way there, you can see, I mean, it's bulldozing young trees over. And what Ken and I are looking at here, actually, these small saplings there. If you zoom in there, trees that are probably a year or two old, maybe 5 years at most, are actually being pushed over and broken by the toe of this slide. And they're not growing out of it and looking for light. It's quite common to be at the toe of one of these features that's actively moving like this, again, episodically, and see it actually breaking these very young trees. So the idea here again is that this is slowly but surely moving along. It's likely that the logging has again influenced the shallow hydrology, and that may be helping things along. But at the end of the day, that type of colluvial failure in this topographic and structural regime is something you see time and again. If you look at the point of the arrows there, this is a new location, probably a kilometer or two west of what you just saw. See a couple trees knocked down there, but with the LiDAR, there's a very handsome slide here. Disrupting logging roads, so clearly historically active. Just the crispness in LiDAR would certainly suggest that. This one's a little bit bigger, but it has had a component of flow to it, which has made it somewhat more mobile, but not mobile in the sense of some debris flows that we'll see momentarily. What's interesting about that one is that you can see that it had a flow episode there in 2005, and it's pretty cool to see what a failure of that age actually looks like in LiDAR. Go a kilometer or so east of that one, again, a similar regime here, absolutely littered with failures as well as logging roads. Comparable structural scenario here, and that big weathered colluvial apron that is generating all of these slides. One to point out here has a really interesting LiDAR appearance, comparable in overall physical scale to that first active slide we looked at, almost 100 meters in length. What's interesting about this one is that it has no obvious record of movement in aerial photography. So even though in LiDAR it looks like the one that moved in 2005, I actually could not tell you how old that is, but it too is offsetting a logging road grade. So we would put it, within the decades age. Kind of the cherry on top of this view is right up here. Funny little feature that's very subtle, about 200 feet, 65 meters in length. But on the side over here, you got this really cool kind of linear uplifted feature. Ken's standing on it right there. It's a very extensive line of ground rupture, and it's almost like a pressure ridge or something like that. You might think of like the San Andreas Fault around Walnut Creek or something like that, only at the landslide scale. And if you zoom in here, you see these freshly exposed tensioned roots here. Really unusual feature. Before I started seeing these in the field, I never would have imagined something like this existed. This is not something like water erosion. You can see it's actually on the crest of a convexity here. and boulders in this area are actually getting kind of jostled with gaps developing around their margins. So that feature, like the first one of this Piedmont suite, is also very much episodically active, and you could presumably return year to year and see changes in it. By this point, you may be kind of getting the idea here, right? So we've moved a little bit to the northwest, still in that Piedmont zone with topography, but these very low dip lithostructural elements. And if you're looking at that LiDAR within that colluvial apron, you might already have picked up on this slide. Another really interesting to look at, again, comparable scale. And this one too is very representative of what we came to expect from these colluvial aprons in this part of the western geologic Piedmont that almost has a little bit of kind of escarpment-like topography. Really cool internal scarps here. The upper head scarp of the slide looked like this when we visited it in 2021. Clearly ongoing movement. And I thought this was one of my favorite pictures from the whole mapping in the area. This tree is doing its best to hang on here. But again, ground motion is ultimately going to get the best of that one. Now, the examples we looked at there are in moderate topography. Overall relief, maybe 300 meters, 1,000 feet in places. It's usually less than that. And again, slope is pretty low. That Piedmont structure does interact with the Blue Ridge Escarpment, which you're looking at here. There's more steepness and there's more relief. And in this image, there's two very prominent debris flows that you can see there from a 2018 event. Interestingly, they would fit very comfortably within the talk opener slide that, if you recall, was over 800 meters in length. So that's a kind of a fascinating comparison of physical scales. That will never be intuitive to me. But sure enough, if you put that big kind of rock avalanche thing on here, it also would just sort of cover this slope. But these debris flows are of interest because, unfortunately, the one on the left actually produced a fatality. So they are very serious features with very serious implications. And I've marked on there their initiation points. Not much to look at here with the satellite imagery. They're not very big as well, 12 meters or so wide on the one on the left, a little bit bigger on the one on the right. But if you fade LiDAR in, you see that they are sitting on these colluvial benches below these outcrop bands. I'm not going to, put a sort of a structural plane on there. We've done that enough, and presumably you're sort of getting the idea about these low angle compositional discontinuities here that are sort of defining this topography. Now, the LiDAR you're looking at here is actually part of a really incredible study done by Corey Scheib and Carl Wegman. I think this is part of Corey's dissertation. And what was done here is that LiDAR change information was collected actually after these debris flows had occurred. And that allows us to zoom in closer and see what they look like within the landscape. Here you see them with Google Earth imagery, and that is the post-failure LiDAR. Now, the resolution isn't quite as crisp as a lot of what I've showed you, but at the end of the arrows there, you can actually see some little scars. Those are the initiation zones. And if we toggle back and forth, if you keep your eye on the end of the arrow there, you should be able to see where those head scarps have developed due to the failures. It's very subtle. It doesn't take much. These slopes are very loaded with colluvium because of the colluvial source, all of these outcrop bands that you see, and it allows a pretty substantial flow to build up very quickly here. And it's really interesting for us as mappers and people that are trying to understand slope failure, and also to serve the purpose of hazard awareness and risk reduction, to see how very, very subtle features that we might pick up with LiDAR could have produced very significant slope movements in the past. So having data like this is absolutely crucial to what we're trying to do, and it's very exciting to have that LiDAR change that was a part of Corey's study there. Now, everything we've looked at again has been in what we call the low dip Piedmont. We'll step across the Brevard fault zone into rocks of the Blue Ridge, and right away there's just a very different topographic grain there. It's much more rugged. The landscape is much more dissected. The drainage networks are much more complex. And a lot of that has to do with just a different suite of orientations of compositional layering. Everything dips more steeply as indicated by the plane there. Got a translational slide there that's actually in the rock mass. You could almost compare that in some ways to a valley and ridge style feature where a competent zone is translating downslope on something weaker. In addition to that, gives you a sense of scale there as well. I should include that, bigger than what we were looking at in the Piedmont there, but not quite valley and ridge big yet. Got a debris flow initiation zone there as well. And throughout this topography, you have all of these outcrop bands. You can see them all over the place. I've marked a few of them there, but they keep going. Every time you see an outcrop band like that, you can expect to find a colluvial hollow underneath it. Colluvium can accumulate to many feet thick there, even though these are not particularly large areas. And ultimately, that colluvium is very prone to failure in debris flow events. And part of our mapping in this area actually does try to pick up, when possible, on colluvial accumulations like this that are going to be ultimately significant to slope evolution. So we're seeing already a different geologic backdrop that's producing a very different topography, and that's going to be producing a different suite of slope failures. If we compare by size yet again, still those valley and ridge features are going to dwarf anything that this metamorphic rock landscape is going to produce, even though it does have these structural discontinuities that are able to control topography somewhat. Moving just a little bit down slope, you can see a similar effect in the landscape. This one actually has a much more defined kind of dip slope geometry. And I'll put that plane on there again. As you take it away, you can actually see the resistant horizon there, and where the edge is broken. It's almost making a flat iron type of structure here. You'll not see that developed in this landscape to the extent that you might between sandstones and shales, for example, in a dipping sedimentary rock landscape. But suffice it to say that lithologic control is very much acting upon the topography here. And if you're a LiDAR fiend like myself, maybe you're already looking around here and seeing what kind of slope movement you can find. There's a nice one right there. Again, very comparable in its physical scale to the one I just showed you within this landscape. And that's part of the picture I'm trying to paint, is that there are very much trends that you see in these landscapes that are presumably just a product of their mechanical nature that is in turn a product of the bedrock geology. Much bigger, probably slowly moving slope over there up and left. A lot of smaller failures within that area, but ultimately that's on a dip slope as well, and that is doing that sort of translational type of movement down and almost out of the screen. Got an old debris flow scar there up in a colluvial hollow. And again, fundamentally, we're seeing a similar pattern to the previous view, where dipping rocks of different mechanical property are making a significant impact on what this landscape looks like. Now, if you find yourself in your day-to-day job wondering, man, could I do more field work? Would I be happier if I did more field work? Let me take you to this place you're looking at now, McDowell County. That's actually the last two images that we've looked at. McDowell County, North Carolina. This will cure you of your urge to do field work, I promise. And you can probably look at that topographic grain and get a sense why. Throw in some summer temperatures and a lot of mountain laurel. This is a rough place to work. And a lot of that roughness ultimately does just come back to the landscape style that you're looking at here. And it's something that's not really achievable in that topographically rough Piedmont. It's really not achievable in the valley and ridge. This is very much a landscape that is fundamentally a product of the underlying bedrock, as well as its position on the Blue Ridge Escarpment on the Eastern Continental Divide. But that rough grain is very good for producing long run out debris flows. Got two of them highlighted here. I'll take those away again, and you can probably see the steep scarps up here at the several initiation zones that contributed to the flow that has this really interesting scour coming down towards the channel. There are plenty more debris flows to be seen in this view. It's actually very difficult, though, to discern them just because the background topography there is so intensely rugged. You're looking at 1,100 feet of ground length there. This one kept going. It would be hard to know, in fact, how far coarse debris, wood, things like that would have traveled with this flow, but just owing to the steepness, owing to the geometry of the drainage network, it would be safe to assume that its overall length would have been greater than what we looked at from the 2018 event there within the Piedmont geologic realm. Trying to figure out how far these flows actually go is something that we spend a lot of time on, and it has proven very challenging to get a good answer. But suffice it to say, this is a very debris flow part of the world. And a very interesting detail here that I recently discovered in a conversation with a fisheries guy is that the stream network that you're looking at here, where you're looking at the headwaters of it, it does not have brook trout, and it should have brook trout. The drainage basin, the elevation, the topography, slope aspects, everything is perfect to have brook trout. And it actually stands out as a place that does not have them. And it's been an interesting thought to consider if really pervasive debris flow occurrence and the introduction of material into channels, or the scouring of channel beds by repeated debris flowing, might actually be a part of that story. So that's reaching, of course, well beyond public safety, but that is yet another potential application of the information that we're trying to gather here. So we've looked now at the Valley and Ridge, the geologic Piedmont with rough topography in it, the geologic Blue Ridge with rough Blue Ridge topography in it. Now we'll step over to the Appalachian Plateau here, which is a place that through Appalachian Landslide Consultants, I've ended up spending a fair amount of time over the last few years. And it's a really fascinating topography. It's one that I have not had personal experience with prior to these professional engagements, but the sedimentary nature of it, the caprock nature, and just the overall appearance of the slopes is really distinct when you look at it with LiDAR. Really incredible failure here, sort of within the debris flow regime. It's big. That is, of course, comparable in its length to those 2018 debris flows that we looked at the LiDAR change with. You can see that the overall scale of the slope is pretty big. This is also a pretty low slope setting. You're looking here again at something that's going to be less than 20 degrees. And the size comparison here is very interesting because these plateau gorges are really big compared in this case to our Piedmont topography with that active slide I showed you pushing over the saplings. You could almost take that kind of Cuesta Ridge and comfortably drop it within this gorge. So these relative sizes of topographic features is really interesting to me because it's not something that you necessarily appreciate from the ground, but ultimately those physical constraints end up being expressed in slope geometries, and those slope geometries are somehow an expression of bedrock mechanics. So it's all going together, and suffice it to say, the nature of this landscape, the nature of the slopes, the nature of that caprock is very much 100% a product of the geologic details, the nature of the sedimentary section, and presumably some amount of relief production, probably due to drainage rearrangement within the Ohio system. Slopes here, like I said, are pretty low. You're looking at a flow type event there on a slope that's less than 20 degrees. And down around the toe of that where it's been deposited, it's really interesting to look at because you have really well-defined levees, and just the toe itself is a larger and steeper topographic feature. It's like when that came to rest, it may have been quite fluid poor, maybe compared to what would be necessary for a more well-traveled flow. I actually don't know. I don't know how much sandstone colluvium is mixed in with this. I don't know how much intact limestone or even shale colluvial debris can survive on a slope like this. But one way or another, this overall style of failure is something that you see time and again here in the Appalachian Plateau. I thought this was a cool example because it has sort of three different styles, if you will, in the same place. You got a rock fall there coming off of the edge of the cap rock. That has made this kind of bulge here. The way I see that, the rock fall moved and bulged sort of a colluvial apron there. I don't know if that's the case or not. That's what it looks like, as opposed to that being just one big sort of rotational failure. And off the edge of that bulged area, you actually had like a flow type of event. So this is kind of a cool, like bumper cars or maybe chain reaction sort of scenario. But again, it's one that is ultimately precipitated by just the physical layout of this landscape, what materials are where the steep slopes are, and where this colluvial material can accumulate and weather, and ultimately mobilize. In some respects, maybe like what you saw there in our geologic Piedmont, where you do have low dip, sort of cap rock type of features and big colluvial aprons that are themselves prone to movement, sometimes at pretty low slope conditions, just due to the nature of the weathering there. Again, pretty good sized. Fit this one, of course, comfortably inside of the big starting rock avalanche, which is sort of like my scale bar, I guess, for a lot of these features. That's why I wanted to kick this talk off with it. You know, it's such like a distinct looking feature, but it's one whose physical scale makes kind of a worthy comparison, for so many other of these Appalachian features. Favorite slide of the talk here. I don't know if anyone sees it yet, but here we got a debris flow coming off of ultimately this sort of colluvium draped slope below the cap rock, and it goes into a giant sinkhole down there. An interesting detail of this part of the plateau is that below the cap rock, there are occasionally absolutely enormous karst features. There's quite a bit of carbonate stratigraphy down below those capping Carboniferous age sandstones. The Paleozoic section here is actually pretty different from what you see folded up in the valley and ridge, particularly in Virginia. And for that reason, the carbonate rocks tend to end up on areas of greater slope, maybe certainly than you'd find them, I guess, in sort of the point of Virginia, like Coalfield or Plateau, Virginia. I looked long and hard for this, actually. I always thought that there might be like a place where you could see a debris flow actually like captured by one of these big sinkholes. This is it. And again, a pretty good size feature within the overall regime of physical scales that you see here in the plateau. But one that's pretty interesting just in terms of like a sediment transport concept. Ultimately, all of these failures are taking material and they're moving it down slope. And fundamentally, its transition downslope into drainage networks is a big part of how topographic evolution works here. And at least in this case, a certain amount of material is now on a much more complicated path, I guess, towards ultimate base level. If you look around in the background here, there's a headscarp lateral down into a toe, these really rough looking slopes. The majority of slope below the cap rock that you see in this plateau image is going to be experiencing some kind of displacement that appears to be associated with these weaker materials and the colluvium that's overlying them. Even a small feature like this is still quite large on the scale of some of those good-sized Blue Ridge translational slides that we looked at. This one's also quite interesting just because of the geometry of the toe down there and sort of this lobate appearance. And it gives the idea that, you know, that these are single event, presumably fairly rapid events, but something about them, be that the slope, be that the fluid content necessary to get them moving, just isn't quite adequate, I suppose, to turn them into really long run out, rapid, high displacement debris flows like you might see in the Blue Ridge or potentially even in the Piedmont rocks that are at very steep topography along the Blue Ridge escarpment. Looking out over that little feature is kind of interesting to do. You can see it here in the foreground. And again, just get a sense of the ballpark steepness of these slopes that are producing that type of failure. It's just not very steep, and it's certainly not very steep compared to the Blue Ridge examples there. The Blue Ridge examples we looked at are underlain in many cases by meta-graywacke. There's a pretty significant quartz content to that, and it does a pretty good job of propping up a steeper landscape. The sandstones do that in the valley and ridge. This is fairly comparable, though, in terms of overall slope to what you might see in the colluvial aprons there in the topographically rough Piedmont. And I always like to use Google Earth overlays like this. I tend to fade them away to try to look at, among other things, movement history, but the ability to just so easily and fluidly move around, like you can do, admittedly, with Scene in the ARC application, is really useful just for getting a sense of the overall layout of the landscape. So finally, to bring it all home here, I told you way back when in my Google Maps view of the Appalachian Plateau, drew a circle in there. It was like, remember this area. We're going to look at this. When I picked that area, I just wanted something that looked like plateau and gorge topography. It was kind of a throw the dart at the map and see what you see there. And the reason I did that was that I figured, based on how the Appalachian Plateau works, that there was probably going to be a highway making use of the slopes up that gorge to get up on top of the plateau. You can see that highway here, so that worked out pretty well. And I also figured that you would see slope movement probably in association with that highway, if not just as part of the natural geologic backdrop, like all of these plateau examples that we've looked at so far. So how did this work out? We'll take a look. So go back here, got this tight hairpin turn there. So that's what we're looking at here. Going to cover up an area right here that is a very nice slide. Go back one more time here. So bring it in again. There it is in LiDAR. We fade the LiDAR away. We can start going back in time in Google Earth. This is 1990s, I think 1997 or something like that. Don't really see much evidence of that failure there. In 2006, however, it is very, very present. And that's actually what you're seeing there in LiDAR. What's interesting about that, of course, is that, yeah, there's a slide there. That's how it's preserved in LiDAR, being at the time of this LiDAR collection, probably 11 years old or something like that. It's not really that obvious today at all in terms of the forest cover. It's not impacting the road. And I can tell you that because ALC has actually done rock slope work along this very highway. So we have been, of course, all over the Southern Appalachians with a variety of projects, but this thing is just hanging out there, and it's got a neighbor just to the east there. That one's pretty easy to see. And that one has, as far as I can tell, absolutely no reflection in any vintage of aerial imagery I could get a hold of. The preservation in LiDAR looks pretty good, but you don't see any bare earth, any type of vegetation disturbance, anything like that. Will that always be the case? I would imagine probably not. Typically, once these things start failing and whatever was sort of propping this slope up has been compromised, you can probably expect episodic movement out of that. And of course, the cut slope there is not going to make that any easier. And this is just a good example of the sort of thing that hides out in LiDAR, but it's reasonable to predict that you might see something like this just based on how this landscape can be seen to behave. That, of course, has been made so much easier by this 1 meter resolution LiDAR. And Steve and I were talking before the meeting kicked off. You can go look at this just on a web browser right now, just through the USGS National Map Viewer. Get on the hillshade, and you can go look at this very feature. It will be straight down from plan view, but the ability to do that just absolutely revolutionizes the way we look at slope behavior. One more here from along that road cut. Big ugly thing full of internal scarps. Again, there's no evidence of this, first of all, impacting the road today, or even impacting vegetation in any of the Google Earth vintages that I saw. Again, that being said, arcuate scarps up there, hummocky interior. This is very much a slide. It has presumably been altered somewhat by the road cut here, and it would be one at the very least just to keep an eye on down the road. And there's something similar down there on the embankment as well. So being able to to kind of spy on landscapes like this and incorporate with that your understanding how these different materials behave, how landscapes developed on those different materials behave, you can end up with a pretty powerful combination of tools that ultimately end up having a very nice application towards a lot of the things I tried to put in the summary of this talk. There's a lot of infrastructure that passes through Appalachia, kind of connects like East Coast cities with kind of continental interior cities. That infrastructure passes through these areas. Need to keep it working pretty well. If you start shutting down big highways for long periods, lots of spin-off effects. There's of course just the acute hazard that's associated with debris flows. That's something that very much needs to be minimized from a public safety standpoint. Even things like conservation, like the brook trout idea. That was something I had not thought of much, but in that conversation, it turns out that that a lot of time is spent actually trying to figure out what kind of environmental changes might be impacting things like fish populations. And there would be at least, I would say, anecdotal evidence that sediment inputs into channels might be one of those. Everything I just talked about is supported by having LiDAR and having an understanding of these settings and how the materials present within them is ultimately going to impact the behavior of the land there. So to wrap it all up, kind of a summary, you can take a look at all of these different places that we've talked about. All of them have topography in them that is sufficient to produce slope failures. The nature of those slope failures tends to be kind of distinct given where you are. And of course, it has been very exciting for me over the last few years just to cruise around all of these landscapes and sort of learn new ways to see how all of this works and how we can find ways to better work with it as people that have to live here and travel across it all the time. I'll shut it down there. Stephen, looks like we got maybe 8 or so minutes till the hour. Hopefully we can field some questions, but you'll have to read them to me because I can't see anything but LiDAR right now.